In this video, we'll take a look at a design problem that requires using a digital logic function of a higher level of abstraction than our digital logic gates. We've been able to use a Karnaugh map to design for two-level implementation, our and/or, sum of products, or our or/and product of sums, which we could then translate to NAND/NAND or NOR/NOR implementation. In this design problem specifically, we'll look at a 4-bit binary decrementer using full adders. So our first step in the design process is to define the input-output. We can define that with a block diagram, and we show a block diagram here with 4 inputs for our 4-bit binary inputs and 4 outputs. We'll use A and B, and we'll use subscript notation to denote A 0 through 3 and B 0 through 3. Where B is equal to A minus 1. We've defined what we mean by a decrementer. Our next step, we need to define the relationship between the input and output. We can do that with a truth table. Since we only have 4 inputs, that'll give us 16 rows of the truth table. And as we do that with the truth table, we see that certainly 1 minus 1 would give us a binary 0, a 2 minus 1, a binary 1. We have no problem for 1 through 15, binary 1 through binary 15. However, binary 0 is going to give us a negative 1. So we're not really sure what we should do with a negative 1. So right now we'll put for our truth table that we'll put 1, 1, 1, 1 as our result, because that isn't the result of any other of the binary decrementing. Then we'll continue to our design process. We might have to come back to this step. We might have to add an output, perhaps for an error, to indicate that we had a binary 0 as an input and that what our output will be. So we'll address the design constraints as well, because we do have to use full adders. So what is a full adder? We can again look at our full adders block diagram and our truth table that describes how the input and output are related, where the sum is the sum of the 3 bits, and the carry is the carry out when we're adding 3 bits. Well, how are we going to use this exactly? We can experiment with our knowledge of binary addition. If, for example, we were to add a binary 16 to our 4-bit binary number, we'd end up with our 4-bit binary number in the lower 4 bits with that carry out of 1. So what we can realize from this, if we were to add a binary 15 to our number, we should end up in our lower 4 bits with that binary A minus 1, which is exactly what we're looking for. So if we add 1, 1, 1, 1 to A3 to 0, we'll get our A3 to 0 minus 1. That's the decrementing that we're looking for. So we can then experiment with some examples. If we were to add 1, 1, 1, 1 to our binary 10, well, what happens? We get 1 plus 0, which just gives us the 1. Then we get a 1 plus 1, which gives us a 0, and carry the 1. So this gives us 1 plus 0. If we were to use our full adder, we'd get 1 plus 0, a sum of 1, and a carry of 0. So what we want here for a carry in is also a 0. And then if we go to our third stage here, we get our carry in, 1 plus 1 plus 0 gives us a 0, carry the 1. And finally, we're adding 3 1s. We get a 1, and this carry out of 1. And we do end up in our lower 4 bits with a binary representation of 9, and 10 decremented by 1 gives us a 9. Similarly, we can show if we, for example, used a binary 6, we get the result of a binary 5. If we used a binary 13, we get the result of a binary 12. And it looks like our process is going to work, and what we end up having to add together is 3 binary numbers in order to do this, and that's exactly what our full adder does. So we should be able to use our full adder for this implementation, for this design, and then implement it with a full adder. Now we still have the case of the 0, 0, 0, 0. When A is represented by a binary 0, we know if we decrement that, that's a negative 1. So let's just take a look at what happens there. Of course, 1 minus 0, we continually get a carry of 0, 0, 0, and finally a 0. So if we compare all these carry outs here we have a carry out of 0, and here we have a carry out of 1. And we can check to make sure that that would always be the case. If that's the case, then we can use that carry out of the last stage of our full adder to indicate that in fact we had a binary 0 and that our result might be considered an error. So let's then go back to the first step and redefine our IO and add to our IO this fifth output of error, where we have a bar over it, meaning it's active low. We can just use that carry out, and it's only going to be a 0 whenever our inputs are zeros, and we can leave then this output as ones. So then we're good there. So this can be our design. Now we just have to implement that with the full adders. And with our knowledge of full adders, we have a carry into our first stage of 0, and then the carry out of the first stage goes as the carry in to the second stage. And we continue to ripple this carry through till we end up with our schematic of our design. And all we have to do is tie together the 4 full adders to the carry bits. We need to, in this case, in each case, we let input Y be logic 1. It makes sense to be consistent with that. And input X be our A3 through A0. And the output sums are our 4-bit binary output that's a decrement. And then we'll, for the last stage of the adder, we'll also have this ERR as our output. So looks like we're done with the design. We can build it, and we can implement a verification process to make sure it works. And that's easy enough to do this level of design. However, we should also analyze our design to make sure it meets the design constraints. So our design analysis, then, we can just go through and add to our truth table what each of these carries would be and what each of our sums would be at each of the binary stage. And again, just to show for our first row here, if A0 was a 0, then we get our B0 would be 1 plus 0. So that would be a 1. We'd have a carry out of 0. Our 0 and 1 plus 0 again gives us a 1, carry out of 0. So we can check each of our carry outs and our B's, B, carry out, B, carry out, and B. We can check that for each of our binary inputs and verify through analysis that this is actually correct. If we were going to analyze this in the lab and build it, we wouldn't have to check these carries. They would be internal. Again, if we're considering that what we've built is for our block diagram. If we were to draw our entire block diagram around this, our inputs, we have 4 inputs, A, 3 to 0. We have the 4 outputs, B, 3 to 0, and additionally, we have our error output. So if we were going to design a verification procedure in the lab, that's what we would be verifying based on our inputs and our outputs. That's it for this video.